Okay, in this presentation we're going to look at a normal distribution question. So, handcrafted widgets are made in two types, A and B. And all widgets require an initial process which takes a time x, which is normally distributed with a mean of 10 minutes and a variance of 12 minutes squared, which is to say that the variance, the standard deviation, is the square root of that, which is the square root of 12, okay? Now, Type A widgets take a further random time YA to complete, which is normally distributed with a mean of 15 minutes and a standard deviation of 4, which is a variance of 16. And likewise for widgets, type B widgets, a further time YB distributed with normally distributed with a mean of 12 and a variance of 9 square minutes. Here, X and YA and YB are mutually independent. Okay. So the first question is, state the distribution of the total time to make a type A widget and a type B widget. Okay, so essentially what we're doing here is we are adding two random variables here, X and Y. By the way, this is just theory definitions. This is not actually the notation we used when we specified the question. This is general theory stuff. So combinations of random variables. So let's just say this is a definition out of a textbook. Okay. So essentially what happens if we have mu A and mu B, and if we want to combine the variables xa and xb, essentially what we do is we add the means and then we add the variances. Okay, that's what we do. Okay, if we're subtracting the mean, or getting the difference between one random variable and the other, okay, and classifying that as a random variable, essentially what we do is we get the differences of the means, but importantly, we still add the variances. The variances are always to be added together. That's it. Okay, so watch out for that. This is the subtraction of the difference. So this is the scenario that we're looking at here for both cases. Okay, so essentially what we do is just add the means for X and YA and X and YB. Okay, so the mean is 10 plus 15 and the variance is 12 plus 16. So overall, the total time for A is the preparation time and then the finishing time, and that is a mean of 25 and a variance of 28. Okay, likewise for the total time for B, the preparation time, which is common to both, and then the finishing time for widget B. So it is 10 plus 12, 2 plus 9, 12 plus 9, so that ends up as a mean of 22 and a variance of 21. Okay. So two particular widgets take up the same time in the initial process. If one is of type A and the other is of type B, find the probability that that widget A was completed first. Okay, so this is another way of asking this, is that we're just looking at X is the same for both. Okay, both seemingly took precisely the same amount of preparation time, but what was the probability that one was completed before the other for the finishing time? Okay. So this is what we're looking at here. YA is less than YB. Okay, little bit hard to sort of parse that immediately, but if you consider like we're dealing with additions and subtractions, that's how we might rephrase it there. Okay, so once you're at this point, you're sort of have the back of this question broken there. So it's essentially, this is what you need to get at. Okay. So essentially what we do here is the finishing times of YA minus YB, okay? And that's normally distributed with a mean of the difference there, that's the difference. That should be a colon there, never mind. So the difference is 15 minus 12, that's the mean difference, but we still add the variances, okay? So the differences in terms of the finishing times are normally distributed with a mean of 3 and a variance of 25. Okay, so what we do here is we get the z-score, 3 minus 0 over 5. Okay, and sorry, 0 minus 3 actually. 0 minus 3 over 5 Here, 0 is what we're interested in. Mu is 3, so it's 0 minus 3. That gives us minus 0.60. What's the phi function of that? From the either statistical tables or software or whatever approach you're using, you should get an answer close to 0.2743%. If you're not familiar with this, it's the phi function, and it's the cumulative distribution function of z. Okay, now you might have done that in used statistical tables to find that, but you could also use software such as R, the R programming language. Okay, so hopefully you should have mastered that already. So we're going to move on from that. Find the probability that a randomly chosen type A widget has a shorter completion time when compared to a randomly chosen type B widget. Okay, so this is the same question again, but we're sort of not assuming that they both had the same preparation time at the start. So it's WA total time for A, WB total time for a widget type B. And again, it's a sort of a variation of what we've just done before, but we're looking at the total times here. So essentially, more or less doing things the same way. Total time here, WA minus WB. The mean there is 3 and the variance is 49. Okay, so this is coming from this part here. Let's just go back here a second. So these total times here, this one here and this one here. I'll call it W here. I'll call it T here, but I'll just call it W here, just to go back a bit. Widget A, widget B. So there we have it, 3 and 49 as the mean and the variance. So straightforward z-score calculation, 0 minus 3 all over 7, which is the standard deviation, minus 0.4285. Working that out, we should get an answer of 0.3341. Okay, and yeah, that's how I calculated the z-score there. Just a reminder that the standard deviation there is the square root of the variance. Pops up a lot. Okay, so that's grand. Now the next part. Widgets of type D are packed in boxes of 16. Now, if you see something like that, immediately think sampling distributions. Okay. Find the probability that the sample mean completion time for a box of 16, okay, of type A widgets is less than the box of type B widgets. Okay, now essentially what we're doing here is the variance of a mean. Now here x is just any random variable x. Okay, is the variance of a mean of from a sample size n is computed as mean of the variance of x divided by n. Okay, so essentially what we're doing here is dividing by 16. Okay, so that's the key thing here, this part here, just remembering to do that. So the variance of a mean of a sample size, just taking repeated samples and calculating the mean from each sample of 16 is just the variance of the underlying random variable divided by the sample size. So that's what we're doing here. The mean stays the same, by the way. It's the variances change. Okay, so it's 28 is the underlying variance. So 28 over 16 is the sampling distribution of the mean for a sample size of 16. Okay, so working out pretty much the same way as we done the last time. Essentially what the key difference here is we're updating the variance from part D from 49 to 49 over 16. Okay, so rather than a standard deviation of 7, it's now 7 over 4. So the z-score would work out to be 0 minus 3 divided by 7 over 4 minus 12 over 7. Okay, just using a bit of mathematical rearrangement. The z-score should work out to be minus 1.7143. Get the phi function of that, and we should get an answer of 4%, 0.0432. All right, we'll leave it there.